post them. Where should I in the lecture at Siegburg?
No.
Where should I pull them? Where?
You could think. You didn't open the channel.
So like
Yeah.
too easy. That slows my computer considerably. I have that my notebook. Yeah. Ist langsam. I need a fast computer. This one just to be it's good for traveling, but no, it's just down. What now? Should I start? I can't.
Just one question to which
You blocked my computer. Yes.
which Wi-Fi network are you connected to?
Which Wi-Fi network? I see it. Okay. Friendly WLAN.
No. Can you connect please to the conference?
Yes, I can.
Friendly 3.
With the underscore.
Friend.
No.
No.
Oh, this is 2.
Ah,
Okay,
shit.
fine.
What was it? Friend.
Really? 2.
Underscore 3?
No, it's just.
Yeah. Yep. Okay. I don't know what. This is Marcus. There's Marcus. Marcus. Oh. I can start anyway.
We can't really see you well.
You cannot see me.
It
It's
looks
a pity.
more like a connection problem.
Okay, seems to work.
Yes.
Am I still sharing?
No.
Uh-huh. Yeah. I just sent them on Madam. Titled, "This is Marcus Abel's talk."
Okay. You see Mathemos now.
Yes, that was the question. Should be uploaded, shouldn't it?
You can just click into the text field and just press enter again. That moves. Or is it control?
Yeah, it's shared
Okay.
Okay. Then let's go.
Welcome everyone to the fourth walk today. It's Marcus Abel, talking about stochastic processes and their estimation.
Thank you. Well, glad to be here and present some of the things we are actually doing on a daily basis. So we often have spatial temporal measurements. I apologize for the non-fancy talk with no pictures, but I feel quite well because it seems that this is code-oriented. So it's not so bad not to have nice images. At least it's accepted. So in many of our works, we have a database. We build database applications maybe from the background, what we have is I'm working in a company where we build platforms, mainly cloud platforms, and all of them are faced with incoming data, processing these data in a more or less fancy way, and then sometimes build models and then publish them on a website. This ranges from automotive to energy-related tasks. So in general, it will become a bit abstract now. We consider spatial temporal measurements with or without measurement noise. So what we have is often particles. We as well have time series without any space. We have time series with spatial information. We have space with time information. So depending on the point of view, we analyze these data and build models or just build statistics from them. So I will focus on the estimation of typical characteristics. So, and the main question I have is, how do I test hypotheses? I will not formalize this testing stuff. I think that would be out of place here. If you want to have models which work, then it's there are. So I will talk with Python examples. So in many ways, we have then hypotheses like this is a random process and it's Gaussian distributed, or this is we have a diffusion process and this diffusion process should be in this and that range. And then we have to test the methods that analyze our data. So we get data, and the data most often are crap. So we have to find out where are the limits with where I can say, okay, with a certain confidence, this model is true or this model is not true. And so the trick is then to build the right methods and test these methods based on data where I exactly know the outcome. And this is where what I want to talk about, how to build the data in a way that you can that you have testable methods which later can be used. We use for testing, we use PyTest. I don't know if many of you have worked with PyTest. Does anybody know PyTest? Yeah, okay, very good. So some already. It's a formal way how to ensure that if you change something in one method, all the other methods still work. So instead of, so your code should be decomposed, and that will make yourself safer as well. If you write a thesis or a master thesis, then it will help you to rely more on your code. So what we do typically is physics-informed data analysis, where physics-informed as well means sometimes chemistry-informed or biologically informed. So because we have as well tasks where we analyze animal data, so not only them running around, but as well the typical characteristics of their health status, related sometimes to their motion. So this is very important. Cows seem to need to move, strange enough. And so this is something where we are faced with. So in general, I would say we have prior knowledge and guess some processes and models. Another field where we have strong analysis running is on atmospheric dynamics. So one very, sorry for the typos, one very strong motivation for me was to understand the motion of atmospheric fields like velocity or like temperature fields, which then move on the Earth. We heard yesterday from Martin, very nicely explained how one can do data analysis with artificial intelligence. So I will focus on the bottom and not go so deep, but there we have as well a very complex problem. I will not go into detail with that because that would be too much theory involved. But we have anisotropy in horizontal and in vertical motion, and now we have to build up a model to which then must be confirmed. So that is the task where we want to, we said, okay, we need an analysis suite. and we will need to test the methods with suitable data. So that means in this talk, I will progress a little bit. I will talk a little bit about theory. I hope that will not be overloaded. Talk about random variables. You should know about this because it's important. If you use random variables for testing, you can as well miserably fail. If you don't know this, then there can be really problems with random numbers generated in the computer. If you add to a random variable time and space dimension, then you end up with stochastic processes, and then where I will dwell most of this talk is actually on diffusion models. So eventually, I want to understand how good is my model that I inferred. So if I have a diffusion model, I want to know how good are the characteristics. This is highly relevant if you think about atmospheric tracers. If let us assume we have a catastrophic event where some chemistry exits factory, and then air is still or almost still, and then diffusion spreads the whole, or advection diffusion spreads a chemical cloud. And we need to know how fast that goes. And that, of course, means we have to estimate how the diffusion coefficients and the advection term, how fast a drift occurs. So let us start with the random variables. So they are used in many physical situations, from geophysics to chemistry to chemical physics, to simulate stochastic processes. So we think that it is very important to understand their characteristics, and so they are, so to say, the simplest building block of a data set. All our data have measurement errors, so already there are some random variables involved. So on a top-level view, we have some set of possible values. We have a probability distribution that might be equally distributed. All values are equally probable, like on a dice, or they might be Gaussian distributed, like typically in a measurement device, because measurement noise is identically distributed. So we can use axioms and these things. This is a nice theory, and we can use it to build our characterization of a process in terms of, say, moments. This is basically the core ingredient of probability, where you can describe the mean value. That's always what you want to have. You say, in average, this cloud, my chemical cloud, will move with a speed of 1 meter per second, or 10 meters per second, which would be bad. But then as well, we need to know what is the spread of this cloud, and that involves the variance. And if it's not exactly equally distributed left and right, we have a skewed, so-called skewed distribution. That means my cloud will be a bit more to the left than to the right. So the center of the danger will move a little bit different than if I would plot simply the cloud. Yeah. So we have first, second, third, and so on moments. In nature, it's easy. There we have random numbers which are generated, for instance, by transistor noise, quantum fluctuations, or other physical or chemical processes. I tell that here because if you really want random numbers in some computers, there is a random number generator built in which depends on physics. So you can plug in a device on your motherboard and it just generates noise. And this noise is very, very noisy in the sense that it's a perfect realization of a random number. This is not so ridiculous as it seems, because if you have big data, you know that your computer has at most 2 to the n numbers. 2 to the 64, that's 10 to the 21 roughly, because 2 to the 3 is 10, so we divide by 3. 10 to the 20 is a huge number, but if you think about Earth data, for instance, if you have a grid with 10 to the 18 grid points, we are already there. And that means we have a repetition of our random number generator if we want to mimic that. Yeah, so that's a limited thing. And the typical random number generators you have works like this. You just choose an initial value, xn, x0, and you multiply it and add some number. You do that for a very long time, and after 2 to the 64 steps, you are back to where you started. This is actually kind of chaos generator, and you see already, if you don't choose A and B right, like A equals 1 and B equals 0, means you have a fixed point. You always stay at the same point. If you choose A equals 2, B equals 0, this just goes away. I will show the pictures now, so you can choose different modulos, different numbers for the fixed point for these A and B's, and depending on them, it is more or less random. This is the basics of how your encryption in your chip. If you go to the bank and insert your Visa or whatever your EC card, the encryption basically works with that algorithm. It is just turning around a wheel and then finding a number. And the art of turning the wheel back means the decryption that is only known to the bank, because the bank knows A, B, and M. So that's the basic ingredients. If you know these numbers, then you can infer back. So you see, these are the examples I just told you. Here, if I have this, I have a periodic motion, and if it's not exactly equal, like B equals B is some irrational multiple of A, then we get a chaotic motion and we get good numbers. Other number generators work with squares and cubes, but it doesn't matter so much. So if you want to see how good the random numbers are, then you calculate the so-called autocorrelation, and I assume silently that most of the people here have heard about that. So you multiply the time series by itself, but shift it, then you will find out, after a certain number, I get the same number again, and you find a peak if it's periodic. So as an anecdote, we had a publication on theoretical paper. People published it, and the results were completely inconclusive. And we then tried to build it and had a certain number generator where we initialized with one number, which was completely unfortunate. And this was the number they used in the paper accidentally. It was something like 1, 2, 3, 4, 5, 6. And that was accidentally a very bad number. So they found periods in a completely chaotic process, not because the process was chaotic, but because they had chosen a bad initial value for their random number generator, and that led to, of course, a big mistake. So it was not just a simple. It was actually published in a very prestigious paper, and it was resolved afterwards. But this happens. So if you really cannot explain your results, if you use random numbers, you can consider just change your initial value. I guess many people know it, but I just want to tell it again. So let us, this should be as well hands-on. So what you do, if you have random numbers, you can use in Python different either NumPy, or later on I will switch to SciPy. So there we have statistical modules for random numbers, and NumPy is actually pretty good. So they have very nice and very efficient random number generators, and you can inject them in SciPy as generators, as we will see later. So here, this is a Laplace distribution where I add them up. And what happens is, well, this is not what. If I now run this, I see that this is a very steep, so it's not exactly Gaussian because it's peaked. That's a Laplace, so it's just a starter. For Gaussian values, we can say we generate random normal. That's a normal distribution. So we have now many different numbers. Sum them up, bin them in a so-called histogram. So, and that indicates you, here you see, we will have that many times in the talk. We will have a certain distribution of values which you can check. So you can check results based on your input. You know exactly your input or the statistics of your input. And here I will show you what happens. What I do is I generate many uniform random numbers, and then I add them up. And so you see that's the uniform distribution. And what I want to do now is I want to sum them up and show what happens if I sum up only many of these things. So I do that in a loop for 10, 100, 1,000, and 10,000 data here. And always sum them up. You see here, I okay, sum up. And what you see is actually that the result you get for mean values, they get more and more accurate if you calculate mean value and variance just by the typical number. So the default, the true values here, the mean value should be 0, and the variance should be actually 1/6. That's not true. It's a bug. Ah, no, it's the relative error I plot here, print here. Okay. Pooh. That's good. So let me plot these values in a row. That was already commented. You see here, mean value of these should be, of course, 0.5, which is getting more and more exact if you take more and more numbers. But as you see as well, it's not really a big effect. For 10, we have already pretty good mean value. Then for 100, accidentally, it's just 0.56. It's not much better. But then for 1,000, it goes to the third digit. And for 10,000, the error is still in the third digit. So it's 0.5. And this shows as well the effect. If you want to get very exact results, you need sometimes n to the power of dimension, or n to the power, in this case, n to the squared, more numbers. This is really a problem if you deal with diffusion processes or any measurement errors as well. How long do I have to measure, even if I have a spatial field? How long do I have to measure until I achieve a certain accuracy? To reduce the error, I have to square the data always, and that is really a problem. Not only for these statistical things, but as well, if we talk about probability distributions, we as well have them as the basics of any machine learning algorithm. So if you use artificial intelligence, then it's not enough often to just double the data. That is what many machine learners do. They say, okay, I have not enough data. Instead of 1,000, I take 2,000. But that's not true. They must square it. And instead of 1,000 images, they have to process suddenly 1,000,000 images. And that's not a joke. If you consider the complexity of these networks, that's a lot. And that is as well why Google and Facebook and all the others have so much impact, because they have so many data. They know about this problem with the squares. So if you see the relative accuracy, so I take the estimate value divided by the true value. So I subtract truth and estimate and divide it by the truth. So it's a relative error for both for second and first moment. You see here it's 0.1, 0.006. So it's still basically 0.1 in the, even if I have 10,000 data. I don't use much more here. For real tests, you have to use more. But here, if I go for a square, obviously it would take too long for a talk. Then probably some of these routines would not finish before the talk is over. Yeah. Here I have put an example. So I say here we have a maximum random number 2 to the 31. This is for a single precision computer. So we have a bus of 32 bits, 2 to the 31, because 1 bit is gone for the sign. And here, what I define here is an implementation of the standard random number generator from 1960. So it's old, but the principle is still the same. So I just return next. This is a kind of generator I write for my random numbers. And here I generate 100,000 numbers. So I fill an array. And then what I say is I want to sum up these. This is a kind of linear random number generator. As I showed you, it's 8 times. So here it's 9 times a certain point in X. So in my field, 2 indices to the left, then 1 index to the left, I multiply by 6, and I subtract the original value. So it's a linear random number generator, and I take the maximum of which I can take. So I say this % means it's the, what's that called in English? Modulo, thank you. It's the module of modulo rand max. So, and if this is a good number generator, this k should, then you can predict what should come out. It should be a certain very, very high number because you just sum up random numbers. In this case, if we run it, we see that the sum of these random numbers is 0. And that means accidentally, I mean, it's not accidentally, I knew. Okay, you don't see it if you plot the distribution. But if you consider the correlations between these numbers, then you see that there are correlations. Obviously, there's a second order correlation between these three, this triple. I have to stand up because I like this. I like if I have the possibility to move on the, but not now. I will wave hands and stand up later on for some moment. As I said, we have, in principle, if I take random numbers and sum them up, then I get automatically a Gaussian distribution. And I can do that for any random numbers. So I take evenly distributed numbers, or I can take Laplacian distributed numbers. It takes a longer time until they converge to a Gaussian distribution. But that's something you should keep in mind if you analyze data and you sum them up, then eventually measurement noise will always go to random, to a Gaussian. So here you see I mix up styles. Actually, it's not completely, coding-wise, it's not completely nice because I use sometimes NumPy fields, sometimes I don't. But anyway, here I generate random numbers, normally distributed, equally distributed. No, this is normal distributed between 0 and 1. And then I sum them up. Yeah. So what then happens is I get the normal distribution, and I can do the same. Okay, this was not some, here I generate my random numbers, and below I just sum them up. So you see I generate random numbers between 0 and 1, normalize them, then I sum them up. It's only 8, I think. How many do I have? I don't know. I think it's just a very small number. And if I run that, yeah, it's eight different random numbers, and it's already pretty nice Gaussian. I do that very often. So that's another way to generate Gaussian distributed random numbers. You can here, what I want to show here is as well how you bin correctly. If you use Python, you should actually, I am favoring the histogram function of NumPy. So, and one thing you often miss is that you get back the bins. So if you use histogram, what you do is here you see you just choose a certain number and count how many numbers are in the bin, and then you sum up the number and plot it. You have to center the bins, and then you will get an excellently fitting curve. So this is very nice, and you see this is achieved by, again, by 100,000 numbers. If I only put 100, you see this is something where I get really problems. It's complete nonsense because this exponential distribution is working badly because in the tails, the events are very rare. So if you have non-Gaussian values, you have to really consider that your distribution must have many, many data sometimes. Yeah, you see with 10,000, it works nice. And before we had 100,000, and that is actually the number where you can say, okay, it fits. Okay. So far about random numbers. Let us see how do you achieve these arbitrary distributions. So you have now measured a variable in, say, again, my chemical cloud. I know there's wind, the cloud is somehow a bit stretched, and I want to understand what is the distribution and want to fit it. So I can generate data with arbitrary distributions. I think this picture says a lot. So what you do is actually, if you have a higher probability, you have to somehow stretch your axis. So what you do is you stretch and push your y-axis together. And if you know how to stretch and push, then you just can transform your data. You redistribute your data from this stripe to that stripe, and data from the neighboring stripe to here, such that your y-axis is transformed. And that way, once you have started with a good initial random number generator, you can generate any arbitrary probability distribution. That is in most of the processes we consider, apart from the animals, in most of the spatial processes where we have, we consider, for instance, wind energy, where we have windmills, there the data are completely un-Gaussian, and they are really completely skewed. If you measure velocity, speed, wind speed in the atmosphere, of course it can't be Gaussian because it's not possible to be smaller than 0. And you have a very long tail, so you have probabilities, you have these extreme events, and we as well use popular methods to estimate these things, how a windmill can produce energy from wind speed. So this is highly unnormal, and if you have as well a non-Gaussian process, that means you shift your estimate from the mean value. You have a completely different most probable value than you see here. Your most probable value is around here, and for a Gaussian it would be somewhere else. Yeah, so maybe the mean value is here and your most probable value is here. So if you have skewed distributions, that is very important. So the basics are these random numbers. You have to be careful to choose right number generators. Even the normal ones are not so easygoing. Now, as I said, we have most often we have processes involved. A process is something where you have time involved. You step from a certain value to the next value, to the next value, to the next value. And if you have a time dependence, then formally, if you write it down, you say, okay, instead of a random value, random number, random variable with x here, instead of p of x, you have now a parameter t. So for each time t, you have a certain distribution. This can be completely deterministic. If you have a delta, if you have just one peak and that moves, it's as well still probability, but with probability 1. It's a boring process. Okay, so if you have to check if things are correlated, and you can do that again using the correlation function. And you can as well check independence if you have a certain probability, and you check if the multiplication of, in this case, 2 times, probability estimated at a time and another time, if these two have the same, can be decomposed such that they multiply. In general, if you have many variables and many times, so you can check independence of your time series by just trying if you can multiply, and that is one way to do it. General processes, you can figure out, this is just a random thing where I wrote down some absurd things. You will not encounter them, and this bracket should be closing here. Yeah, so these are processes with delta function, means you have it exactly at one point in time. It's not smeared out. So if you now want to test the independence in time, then you have to calculate the mean of these two multiplications, and that means you just check if the mean values multiplied are the same, then multiplied values, and then averaged. If you want to test if things are stationary, you can as well compute p of x t1. This should be some p for all t1 and t2, and we want to do that now. So we had this is again the IID assumption. So for exponentially distributed numbers, I already demonstrated it. So if you want to have really high accuracy, what I want to show here is if you add these random numbers, you achieve a Gaussian, and good it is, you can see often only in logarithmic scale. So if you have e to the minus x squared divided by some norms, then you see deviations in this Gaussian. If you see it here, that seems perfect. if you see it here, you see we have some problems in the positive values. And this is because I generated it using exponential numbers. That, of course, goes away if I use more and more numbers to generate the Gaussian. But here you see that in the positive tail, you have some problem. This is, of course, not Gaussian, and you can detect these things. So you should plot things. If you want to go for high accuracy, you see here 10 to the minus 2. This is something you don't see by eye. Yeah, here, this is the problems are here, and these things are basically 0. If you go for very rare events, then you see them only, or of course you can do many analyses or other analysis, but if you want to visualize data, then just plot them on a log scale, and it's much easier to detect differences. Yeah. As I said, this is due to the generation where I plotted, where I took the exponentials as a basis. Yeah. Okay. Let us go for the processes. If I have diffusion in one dimension, so I say I start somewhere and then I choose a random step to the left and to the right, and then I do that again and again and again. So here I do that at the moment, at this point, not with NumPy indexing. I just write a for loop here, just for better visibility. I choose a certain point, 0. I start with 0, and then I evolve many trajectories at the same time. If you do that for data analysis, so what I do here is actually, except for the generation of my test data, I do exactly these steps with many variables we have, like, as I said, velocity or the absolute value of the speed, wind speed, or temperature, or other things. So I do exactly these things apart from generating the numbers I already know. So I use these methods really on for my testing. So here I have n equals to 5. So I have 5 random walks, and what I show is first the random walks. So this is how it looks. Fancy. So this is, see, it doesn't look really like this would be completely random. If you see these data with 5 data points only, you say, okay, there's a regression and the lower one is an outlier. Of course, if you take many, many more data, see that everything is security. So what you can do is you can calculate these moments. So mean value, variance, skewness, and flatness, and even higher moments. And in order to visualize a little bit, so here you see this is the second moment, this is the expectation, and now it's 5 trajectories and not 100 because I set it to 5. So you see it's only for very limited time we get a kind of expected behavior, and then it deviates. This is what you see here. So you would say, okay, this is somehow deterministic. There's no randomness in. If you calculate the moments, so that's the characterization of my distribution, it's very nice for lower moments. We have a nice flat line for the third moment. We have it's 0. So the third moment must be all uneven moments are 0. The odd moments are all 0 because of the Gaussian symmetry. So that's easy. If they are non-zero, then so the interesting things are here, this orange line and the red line. So you see for the fourth moment with these few data, we still have a very nice flat line, but for the sixth moment, fluctuations get so high, and this is get very high, and this is exactly what we saw before. If you have not enough data, it's not really Gaussian, and this fluctuates forth and back. So this is very, it's a very nice visualization, in my opinion. So, this was diffusion in one dimension, but since I'm here in a geo-oriented conference, I wanted to go as well two-dimensional. So two-dimensional Brownian motion is something where you have to understand the laws. And here I stole the Brownian example from SciPy and want to go with you step by step through this, through the implementation of that function. So, and before I want to go back here and tell you what we have. So we have as a property of this diffusion process, we often have the so-called white noise that's denoted by this symbol. And if we do a little bit of computation, people who like it might redo this. So you can calculate the autocorrelation, and having the Fourier transform of the autocorrelation, you get the variance. So you see that these two things are related. This is actually why I wrote it down again. So if you calculate autocorrelation of a process, or if you calculate variance, this amounts to basically the same thing. It's very interesting and a very deep connection between going to spectral space and to real space. And computationally, you might know that the Fourier transform is very efficient. This is why I mention it here. If you want to calculate a correlation by yourself and don't use the prefactored methods, try to evaluate things using Fourier transforms, because it's n log n instead of n squared, and that makes the hell of a difference if you have big data or very long time series. It doesn't stress so much your patience. Yeah. Okay, so having a variance, you have the autocorrelation, and having the autocorrelation, you have the variance, basically. It means if you calculate the spectrum of such a process, it's flat. I don't do it here, but this might be something you may consider for doing yourself. Generate a random process and Fourier transform it, and then look if it's really flat in spectrum, in spectral space. And if it's flat, it's a good process. If it's not flat, it's an awful process. You can use that as well to check the quality of your data. You can use it if you Fourier transform your data. That's one first thing you can do. Then you immediately detect periodicities, and you can filter them out if you want to only concern noise, or you can filter out the noise, and then you are left with your periodicities. This is a very powerful technique. If you add up things in Fourier space, you can detect periodicities. This is, for instance, how the satellites transmit the GPS signals. Just as an anecdote, I know that after 1 hour, one should tell something different than equations. So the power of averaging is in the GPS signals. So you get you have 1 second per signal, and then it repeats. And in this 1 second, every satellite transmits a signal, where it basically it transmits its ID. But if you measure one second of the signal, it's complete noise, because it has to travel through atmosphere. Atmosphere just noisifies the signal, and then you don't see it. But what you can do is, because you can chop this 1 second into 1,000 pieces. So, and that's the frequency with which the satellites send. So they have millisecond resolution, and in this millisecond resolution, they send each millisecond, they send again a signal, which is, I think, 32-bit to, well, no, 64, I don't know. It's a certain number which is low, maybe 100, just to fit in. And then they add up the signals. For each millisecond, they add up these signals, these 128, say, bit. And after a while, you see, if you do that, you see the signal coming out very nicely, and then it's a certain number, and that's the ID of the satellite. So if you treat noise in the right way, then you have really powerful things. That is as well how messages, I mean, I already said at lunchtime, these things for transmitting messages is very important for many, many different applications, from traffic to military. So I'm against military, so we don't deal that, but I know that all these things, as well the GPS improved information, the military uses just kind of transformation from noise to signal. Yeah. If the signal is dependent from time to time, like independent, like it is for the GPS signals. After 1 millisecond, there's another signal which is completely independent. Then this is called a Markov process. So if x of tn does only depend on the previous step, it's called a Markov process. If it doesn't depend on the previous step, it's called independent, of course. So, and this allows you to understand if your process has a memory and how large your memory is, how deep your memory goes back. So if you want to understand if you have a dependence, you analyze the conditional probability of a certain time point, your variable at a time point, given your variable at a previous time point. It's a kind of, if you want to, if you have a drift in your data, in your diffusion process, so you move along a certain trajectory and you have measurement noise, then you know that your current position depends on the previous position because you just move with a certain speed of 0.5 kilometers direction northwest. Then you know that, and this memory is lost after a while. And this is exactly where you use this Markovian property. Yeah, that's a remnant. So let us check what a particle does with drift and diffusion. Yeah. So this is the basic motion of a particle with measurement noise, or the basic motion of a particle in air. Yeah. It's like a Brownian particle, or like a walk on Wall Street. So if you have financial data, often they are pretty much Markovian or even decorrelated completely. So for some reason, numerically, you can solve it if you say x, the state of a time, of the next time, equals the state of the previous time plus noise. And for peculiar reasons, you have to square root the time interval. Because, why? Because the diffusion constant is defined as delta x squared divided by delta t. So x squared t, and if you try to understand that, so if you x square here, if you have an x here it's here square root of t, if that would be x squared, then here you would have a t. So that's the essence of diffusion. It's very important. If you don't do that, you don't get the process right. Let's do that. So now we generate Brownian motion, not, oh, I have a picture, so I want to show the picture. If I prepare it, I want to show it. So this is 4 particles, and it's for 5,000 time steps, and you see these 4 particles go apparently in completely different directions. Whereas if I step 1,000 steps, I drift to the upper left corner with a certain probability. I chose not to go plus. I chose, that's 6.5. I corrected that. It's a misprint. So with a certain higher probability, I go up. With a certain lower probability, I go down. So each step I take a step size of 1, and you see it drifts. But along that drift, it's still pretty random. That is my chemical cloud in an abstracted way. So if I want to see if my methods to analyze chemical clouds are correct, I first program this with known random numbers, random processes, stochastic process, diffusion, plus drift. And then I can see if this corresponds to what I have measured. So here we have the Brownian, as I said, we have the Brownian implementation given by, as an example, by SciPy. Yeah, thanks for that. Actually, the author is not mentioned, so to anonymous. So as an iteration scheme, you see here, what I have is I have x of t plus delta t equals x of t plus some distribution, zero mean value, and delta is my delta x squared times dt. And the input value, the arguments are my initial value, how many steps I take, what's the time step. And then here it's the, so to say, delta is the average step I take in x direction, my Brownian motion, and then I have an output. This is not how it would work this is really a testing function. It's not how you would implement it for processes which should be evaluated on the fly with time. Why I like this implementation is because here you see this is the stats module, and it's very helpful here. Just show you what it contains. Cluster. Where the heck is stats? Yeah. So there are many statistical functions, very helpful. You see, it works with most of other packages, yeah, and one is the stats models where you analyze. Another one is pandas and geopandas in particular, as I learned today. You can you can prepare your data in slices very nicely with this pandas and geopandas functionality, such that you can apply these statistical models easily. Seaborn is good for the statistical data visualization. Probably you know that. It's pretty good, and you can produce nice plots in a minute. You have the learning part, where so this statistical module is as well kind of basic to scikit-learn, and then this is the Bayesian and Monte Carlo modeling part, where you have probabilistic machine learning, and this is a very interesting part, where basically you can try to model your processes, even as well geo-processes, with statistically. So this has the advantage that it's not frequentist approach. You can update. This is mainly connected to models which you can update. And that's a very important thing, because if you deal with measured data, you don't want to rerun your model every week. You maybe just want to add your new data and get an update of your model for the data. This is a very nice thing, and that is typically done in a Bayesian way. So actually, I think it's the newest of these packages. And for the R people, you see, you have the Python to R bridge. So you can use your R modules in Python, or vice versa, probably too. I'm sure that R can as well use Python in the meanwhile. Yeah, so Ben says yes. So yes, probably there's a Pi to R as well. Actually, I would name this R to Pi, but it's not the way. So here are many different. I just want to go through the module quickly, because I think it's very helpful, and we only scratch the surface. We have distributions, we have continuous distributions, basically all I ever used, plus many I didn't use. Yeah, so there are completely crazy things like this crystal ball. I already clicked through, and I don't even know where it comes from. It's really something crazy, which must be special cases. But others like gamma and logistic distributions, they are there. Very helpful to use them. And you can be sure if you don't use a completely stupid random number generator that they will give you the right results. Same here. So you have multinomial, you have statistics like describe your statistics, compute this descriptive statistics like mean values and so on, what we did already. Then you have special functions which are pretty performant for frequency, so where you just count. You have the correlation functions, different ways, Pearson and Spearman, very well-known ones, but you have as well other ones which are not so well-known. Linear regression, you have tests, and this is an interesting feature which you, if you deal with data, should try out. And then this is, I would say, advanced topics where you generate data in a random way. You have Monte Carlo methods to sample distribution functions. This is efficient in particular if you have higher dimensional problems. If you want to work with your data and you do not what I now presented, do this test stuff, you can use these resampling things, and they provide nice ways to just bootstrap data. You can permutate your data and check if things are invariant to permutation. And then you can again do Monte Carlo tests. So you draw out randomly samples and put them back. That is nice, and it's not evident to do. If you do it the first time, you do it somehow, and then it works, and then from a certain time on it doesn't. So here you can inject other statistics functions and transform. This is as well interesting thing. If you want to transform data, sampling and generation of data, this is as well important because you know it. Distribution fitting, circular statistical functions and contingencies if you have classification problems. So then you plot the tests, I will show that, and you have errors. That's it. So it's a very powerful package, and let me now run through the Brownian stuff. So you see here we have the stats, SciPy stats. Norm means normal values, and dot RVS means you have the random variate sample. You want to have the samples you give as the input array. That's just shorthanded for your for shape. So you add another row because you want to output the data as one more dimension. But the important thing for the diffusion basically is written down here. You have your delta x step, so that's the step left, right, and here you see it's square root of dt. So any time step you have, you can calculate the diffusion constant basically from these two things by dividing delta by the square root of dt, and squaring delta and divided by delta t, then you have your diffusion constant, and that gives you an intuition about how fast you move. You can inject, that's called injection, if you just don't prescribe the random number generator, you have to give that, so your random state has to be generated. This is generated by this stone-old Mersenne twister method. So exactly with kind of special this modulo methods. It's one of these modulo methods I presented before. So the rest means here, this is a trick to do things quick. You sum up the steps because you don't want to have only the deltas, you want to have them summed up, else you don't get far. So if you have only plus and minus 1, you stay at 0, but if you have real diffusion, you just diffuse away and come back. So we have to initialize it. So we say we want to have 0.25 as my maximum spatial deviation times number of steps I go forward. And then I have my delta t, because I don't want to go beyond 100 in time, non-dimensional units. And here, this is the number which is deciding how good my things look. If I have two trajectories, I will step 200 steps, then it will be not very good statistics. Let us do two. So here I have the Brownian, I call Brownian, and the output will go to out. So equals x. So x will contain in the first argument. In the second argument, it will contain my trajectories. So I can slice it in x and y, because I say I want to have a two-dimensional thing, and then I plot it and check how it looks. So here I have my 2D Brownian motion. Here 0, I start here and I end up here or here. So I mark the start red and the end green, so I have two endpoints. That doesn't look like good statistics if I go in space. So let's do better statistics and go here for 2000. That was too much. Takes too long now with the beamer. I plan 10 minutes. Okay, this computer is going down in performance due to the beamer stuff. Sorry for that. Okay, we are done. So it looks like this. It's nicely colored, many different things, and you already can imagine most of the bulk is here at 0, and now we want to analyze that. So I want to make an histogram in 2 dimensions for these 2-dimensional paths. And doing that, I use the histogram 2D. It's coming from NumPy performant. So I have here x and y values, and I have the edges just to have edges of my histogram. It looks like this because it's on a linear scale. So it don't see much. What I did then is I cut through at a certain point, and I can see that each slice here from top to bottom should correspond to a Gaussian distribution. In any, because it's completely round, in any direction it should be Gaussian. And look at this. So this is a cut at, I don't remember. I just took arbitrary numbers, 10. So this is 10. It's more or less in the middle. Yeah. Those 10 steps, 20 steps, I think. So 10 is here in the middle. It looks Gaussian, given the statistics. Yeah, so I don't have much statistics. So this basically is a Gaussian, and if I let it run longer, it looks more and more Gaussian. So I the neighboring point 11, it looks as well a kind of Gaussian. So the statistics here in the middle is not so good. That means I have to tune sampling, plot it on a log-log scale. But I tried before. Log-log scale really doesn't look nice, so I don't do that. So now, question is, I now pretend not knowing anything about my data. I now have manufactured my methods and everything to prepare my data. So I can prepare random data, and now I want to check the basic assumptions. Is my process stationary? Can I determine the typical steps within a trajectory like left, right? And then the result should be random motion in X and random motion in Y. They should be independent. And this is what I now do. So I shift my data by 1. and calculate my typical dx. You remember above it was delta. So I just subtract my one step from the other in the right direction, so along the first axis, and then I expect that I should get a certain distribution for my dx. Gaussian, of course. That's what I would expect. Ah, it's so slow. Stupid. Huh. Sorry for that. I will rerun that. I use the value above for the times. So, but while this is running, hopefully finite time, yeah, you see, this is how my delta looks. So all the different, these 2,000 points on top of each other, and now I can stop. It's still plotting. Okay, now I can take arbitrary trajectories again and average them. Yeah, so I take for every time point, I want to test stationarity. I had 200 time points. Each number here corresponds to time point. Then I take for one slice, I take all the points I have and try the distribution. And look at this. This is for different time points. It looks pretty similar, but how do I quantify it? So how good is this stationarity? I can do now tests for that. So let us take this. I can plot the moments against each other, and this is what the so-called QQ plot does. I do that here. Hope it will finish in a, yeah, because I had it used. So what you will see, this should be a line if it's good. So, but you see here, it's not perfect. We have this is a QQ plot for two different spots. So I took one number at the beginning, one number at the end. And so you see it's more or less, it looks like a straight line, but it's not. So I order these values and they should lie on a line. It's not what they do. So how good are they? For this, I calculate moments. If I calculate moments, I can I take the variance. And since I prepared that as well, since the variance, I skipped that. So if I have the variance, so I give you some facts without proof. So I can estimate the variance. Here, if I have no previous knowledge about mu, I have to divide it by n-1. If I know the mean value like I do here, I can divide by n. For our many numbers, it doesn't matter. Not really. So this is my estimate of the variance, means the deltas. So what I expect, where am I? What I expect is that this the expected value of this variance is actually the true value. And now we can ask ourselves, how well is this variance met? If I have a result of my diffusion is something like 10 square meters per second, then how good is that? Is it 10 plus minus 2 or 10 plus minus 10, or is it 10 plus minus 0.001? So we have as well the true variance of the estimator, and that's the fourth, related to the fourth moment. And then we come to the end, actually. So you see here, I calculate the second moment. Now no longer with my own stuff. I just take the square root of the second moments of the sats.moment module. Same here. This is the formula implemented I just had. In order to make it comparable to the data, I can show it. So I now plot the estimate of the second moment here. So you see, I have 200 data. The probability is probably Gaussian. Expected, this is calculated from what I knew, it's 0.76. 0.176, and what I calculate is 0.64. And the mean squared error I get is 0.06. So I compare these two values, it's just outside. It's not very good. So if I have a distribution of my value, my true value 0.176, it's not so bad, but it's not so good either. So that is basically what I wanted to tell you. We have to finish earlier. This is the trajectory of a shifted of an advection. So my chemical cloud now gets advected, and you can't see it. It looks much more nice if I have more data. So, but what you see is that the curve gets a bit squeezed because now we have a drift in our data plus noise. So this is really what chemical tracers do. They drift because of the wind and they diffuse because of diffusion. And now the next step is you can apply all this machinery again to estimate the drift coefficient by just averaging over the noise, because you have mean value 0. If you average everything over the noise and then you get the drift, you have an advection term, then you can subtract that and you have the diffusion term. So doing all these things, you can very nicely analyze things. And what is very important, if you apply statistics correctly, then you have as well error bounds for your coefficients, which you get out at the very end by calculating the fourth moment. And now the circle closes. I showed you these plots of the fourth moment and the sixth moment. If you have not enough data, many of these analyses are completely useless because your error bars get too big. Fortunately, on Earth science, you have a lot of data, most often. So I can point to the TOA database from Martin. There they have a long time series sometimes. It's very nice, but they are very distant in space. So to correlate things in space is not always very evident. And we tried to do kind of this analysis with these data. It was not very successful because the correlation is lost on the wind speed and on the transport of the trajectories over longer distances. Okay, I want to conclude. I have to with a few notes. Yeah, there should be a few notes. I will re-upload my talk. It seems this is not the version I have updated. I will give it. I wanted to stand up because I want to profit from the mic. So thank you first of all, and then what I want to conclude with is that it's important if you do this kind of analysis. It really is profitable if you prepare your tests based on data you know. If you know characteristics of data, then you can use them to test your methods. If you now would use blindly statistical methods without knowing how good they work, I mean, I built on existing methods from the stats, SciPy stats package. But based on that, I need to understand, okay, if I have time evolution, if it's a Brownian motion, if it's a non-Brownian motion, if it's advection or not. And these things you can really test by building on the well-known packages and test them with good random numbers. You get, first of all, you get a good feeling about your statistics by just plotting them, visualizing data, as we saw with the Gaussian. If you do it on a log-log scale, it looks sometimes much worse than expected. You can fish in the tails of the distributions. You can calculate moments, get an impression from the variance of the moments. You get an impression of how well your statistics is. And if you don't have Gaussian statistics, which is the rule, then you get a good feeling for how many data you need until your line gets straight. So this is a strong visual indication that that you have enough statistics. Sometimes your line is straight and then it just deviates. These things can be really tested. If you have it seen, then you should test it and put it to real hardcore numbers, which you can test, and then you can build up a whole library based on these tests. Say what we did in the past for turbulence. What we will do now is basically for machine learning, we will build probably a test suite based on the things that Thomas Seidler is working with. So just to get an understanding of how many data are needed to achieve good results. So this is really something where you have strong theory behind, but on the other hand, even without theory, you can find out if it's good or not, and if it's not good, you can still go back to theory and dig why it's not good. Okay.